All right. Well, I'm Lorenzo, working with James Glazier in his lab, and now I will follow up a little bit on the concept we have discussed earlier this morning. And just to follow up on the ideas that I saw many questions, some were previously addressed already in the chat, but yeah, many have asked why we should use that extra work of putting things in Python only, why it is useful. And so this is a kind of a rough list on when you want to build via tweeted player. So almost always when it's about building CompuCell3D stuff, purely CompuCell3D stuff. But then when we want to do something else, like parameter searches, simulation outputs in a vast amount of simulation, HPC, cluster things, and especially when we run these so-called embarrassing parallel workflows and CompuCell3D and this kind of simulation are very amenable to this kind of strategy. They are often prone to be using this kind of parallel workflows that involve little communication between processes, and so they can be run in this big computer and speed up the execution. So in the interest of time, we'll skip on this, but I share my slides, and the code that we will be using today is in a folder I've shared already. And this will be, you can use that code. So you won't have to copy my code. You can use that one that I shared, and hopefully will work on your setup. Otherwise, we can debug later. And again, in the interest of time, I will move forward. So a little bit introduction. There is this famous quote of someone famous in modeling saying that all models are wrong, but some are useful. And again, in the interest of time, how do we when do we design, implement useful models? We need to carefully plan control models, input output. We want to make them fair. We want validation and a certain bunch of properties which help out in having this model useful to several in some extent. And to address one of these kind of problems and to one of a few of these features that we want to have, one way is to establish metrics. So like in all experimental science, we want to measure things. And CompuCell simulation in general, CompuCell simulation especially, are no different than any other experiment we would like to perform. So the one thing that we want to know when we have built a very nice simulation, what is that actually our simulation tell us? Which kind of prediction can we do out of the precondition that we set up? And so we want to have interpretable metrics to guide our analysis and perhaps optimization. Okay, so here I kind of, to release a little bit of the steam on a very codey first session, I will try to launch an exercise that is more instead of practical. Here I indicated in one particular simulation that if we have the time we will look at, and that is a so-called angiogenesis simulation. We have a vascular-like structure growing according to certain parameter set, and we can measure certain parameters. Like we might want, if this is a vascular network, we can measure the white holes enclosed by structure. We might measure the length of the green things that are the vascular structure, or we might measure how many intersections do we have, all right? And so we can measure this kind of stuff. So let's suppose we have something more complex. Here I put a toy simulation where we have blood vessels and cancer cell and cancer stem cell, necrotic cell, then they grow following certain pattern interdependently. But which kind of matrix we could think about this? And we can perhaps immediately think about an exercise here and think about it. Think about this simulation and think about which kind of matrix might be useful to actually capture the meaning of this simulation for you. And please reply in the chat if you have suggestion, any idea on this. And even if this simulation is not familiar to you, okay, it's just an example, just think about which matrix will you extract from your simulation. So give me your best shot, and then I will show what I thought about this simulation. Give you a couple of minutes so you can think about this. In the meantime, I'll put the Y again. Any ideas? Don't be shy. Okay. What matrix could be useful? Let's put the slide before, but I indicated those that I will put in the angiogenesis simulation. Okay, no ideas? Well, since the time is a little bit short. Nice, this one. Oxygen level, diffusion parameter versus cancer growth rate, tumor size. Fantastic. This is a good one. Any other idea? Number of cluster, fantastic. That's another one. Number of potential seeds of the tumor. Actually, I thought about some of those that you mentioned. We can have at the simulation level endpoint, in general endpoint of time series method. We might think about something else, but for now, those that I had on top of my head. Simulation level, we would like to know number of cells, number of stem cell, number of necrotic cell, number of clusters as like suggested, oxygen levels at the cell level, diffusion, okay, how the cancer grows. So we might want to have, I don't know, area covered across the whole lattice, and then we can have things in time series. So any of the above over time. So we will see how to do this in how to extract this matrix from CompuCell. And it's not a difficult because you have worked a lot in Python so far, no? So you know that after all, you have all the information that you need in your Python Steppable, and from there you can work a lot. So things that we can do is to think about examples of matrix and method to evaluate them. And so for this, we can perhaps run another exercise and think about a little bit of what can we do? Actually, this is nothing to do with CompuCell, it's just fake data. And this is about what we will do once we gather this data from our CompuCell. Let's assume we have a simulation that give us parameters M1, M2, M3, measure 1, measure 2, measure 3. Let's say this measure 1 might be average cell volume, might be number of cell, or some other matrix with these ranges. And we have a reference metric from our experiment that tells, okay, we would like to have this kind, and this is our standard. So how do we go about, okay, how do I know that my simulation is right? See, that was one of the points. How do we know that, in fact, my simulation that can give this kind of numbers actually yields those that I find out to be truly true experimentally? And so we need to implement ways to extract this metric from CompuCell, and then we need methods to compare those against the standard that we have defined. So here, we don't have the time today to do this exercise properly together, but this is nothing complex, is pure Python. So you have this in your folder, material folder, so you can offline play with this and try to see what I mean. But just to explain one exercise, might want to have these 1 or 3 objectives, and we want to optimize our simulation to actually reach this kind of reference matrix. And for using this, we can define matrix. I listed here a few options you might want to use. You can use a single objective optimization. You can use multi-objective optimization, and we can take some of the metrics that are commonly used. For example, for the exercise, I use the normalized square distance that has certain advantages in respect to other measures. And here you see the code where you can simply we define a function to calculate the normalized square distance, and then we test it. Since it's not too complex, we can try perhaps to run it, but I will probably need to rerun. Okay, no, it works. And so here is just to say, just to give you a hint on one, here I changed one parameter at the time in my experimental test by 10% in the different parameters. And we see that the yield of our experiments in terms of our metrics are pretty consistent if we change the measure the same. But if we change them all at the same time, well, we see changes. And this just to show you how do we get numbers out of many numbers, multiple cases, multiple metrics we want to evaluate, and how to have something we can use in some optimization routine. That's important for optimization, but we can have also the same type of data can be useful for analysis and other things. So if you play around with the notebook, you will see that there are a couple of other examples. If we have data distribution that we want to compare, there is a time series. They don't look very different than data distributions. And then an exercise if you want to try yourself. And the question there is, what we'll need to do if we wanted to formally evaluate how our metrics varies with changing parameters. So do a parameter sensitivity analysis. So we are sure that our parameters are in the right kind of range when we set them up. Okay, so this is a little bit in abstraction, and in one sense, I hope that relieve the steam on pure coding. And this, as you see, doesn't involve any CompuCell3D. You can have, these are just strategies you can use for if you had experimental data of this kind in any field. So now I would pause for just 1 minute, since the time is very short, and then I will dive a little bit again into defining how do we extract metrics in a CompuCell3D simulation, and then I will close. So I give you 2 minutes if you have question or you want to some quick one, flash question that we can address now. Examples, so we can. So there are 2 things that we won't have the time to do today, but this second one follows almost directly from the lecture this morning, and from what we will try to see, time permitting, on this first part on instantiation simulation via sim service. It's like a repetition of what TJ has said, and so I'll probably skip on the import the XML part or just go very fast and look at a steppable that is a little bit become the topic of this extra session. So how we take data out of simulation, let's implement some code that does that, get numbers out, and then crunch them and optimize or do the things that we want to do with our numbers. Okay. I don't see any burning questions, so I will just move forward. So one thing that we could do to keep it as a reference is this. So let's think about it. When we want to go to essentially XML to pure Python, because we know a steppable, which is the other component of a CompuCell3D simulation, is already Python and is a Python class as steppable. What we're doing here, we are turning the XML into a Python class again. This way, we have 2 Python classes, we can use them and run them as Python objects. So what we do to turn XML to Py is instance data sim service described by TJ, we define the core specs. We import Steppable and mitosis, or mitosis if we want to have Steppable that do this. And then we instantiate the service, we define the various bits, and we run the simulation. Here is essentially the receipt, the cookbook for what we need to do. So if you look at the Jupyter notebook that I shared, you will see that there is the usual stuff, all right? A lot of imports. I like to do everything at the beginning, so everything is clear what we've done. Here are examples just for being slightly didactic. We know that we are not using these imports, so I comment them out. If it was in my code, not for teaching, I will just delete them because there is no use to importing stuff that we don't use. And this is just to keep in mind. And then we import stuff that we might or might not use. Not today, for example, we've used these earlier on, but we won't use them today. So, but as before, if you get familiar with the Jupyter interface, we can do this plating. Then we can get along with things that we have seen before. If you have doubts, please stop me and I will just explain whatever I'm doing, but I'm saying that while I do it. Bot score specification. Metadata, same metadata, not much there. Number of processor 1. Cell types. I'm implementing the angiogenesis simulation. I think we have seen 4 matrix that we want to implement. Playing, volume, interesting plugin that I need in my simulation. Contact that I need in my simulation, plus some parameters. But it is fast, but really, you can look at the notebook. It's no big thing beside what already TJ explained. Diffusion solver, the chemotaxis plugin, because that simulation implements chemotaxis, the uniform initializer, and then we want to initialize and run the simulation. You do this, I see that I have an error. Probably I forgot to run something, and I just go back and do that. Anyway, this should work out of the box. So if I run all, I should be kind of fine, and I should have all working. So this is not very, oh, you see, that is started, and we're happy with that. So behind the scenes now, let me stop that so we don't overrun. So you see that I forgot previously to run a cell, so you give me the error, but now it runs and it returns my true. Okay. So fantastic. You see, you're already there. Fantastic. I'm happy that it worked for some. So what I really wanted to go through is a little bit more of the second part. So forgive me if I am cutting short on this, and I will take that someone is already able to run it using the code that it works. So you can play with it as much as you want. But since we have only about 5 minutes left, I want to go through one thing that I think is important, 2 things. So when we try to do everything programmatically, we will have to create, or this is a good way to do that, to create a class that handles our simulation initialization and running. So I put any class, Python class will have an init, and here I put the parameters that govern my simulation. In the code, I try to use docstring, both to show some good practice and to help you figuring out what is happening in the code, some interesting link. But what I want to go fast, you see that this is exactly the copy of what we have done before, just written a slightly different way. At some point, if we have a steppable in our mind, and if we have defined it, we have to register in this way. And we can register as many as we want. This is essentially the middle file in your typical CompuCell3D simulation, the one you never open. This is containing this kind of code, and this is important here. So, but I want to jump to analysis steppable, which we can define here. And what happens here is that I can initialize my steppable and define my step methods. Since it's not useful for us, the step method today, this is a strange case. We always use the step method, but today we don't need it. Or at least we don't need to do anything at the steppable level. But we like the finish method because it's where we implement some data image analysis platform. So especially we implement those metrics that we have seen at the beginning. And I can show them again here. These here, no, number of lacunae, number of nodes, number of branches, network length. And here is the code. I don't have the time to go line by line here. I see the notebook might already have finished. Let's see if it doesn't give us an error now. Let's run it. Oh, yes, it's running it. So if you run the code and you run it with standard parameter without changing anything, you will have in these cells, you will have a return object where you have the parameters, and then you will have what happens with your simulation under this particular parameter, which is not the best in case because, okay, parameters were not the best, but yeah. And this is let me do this again, just for make sure that I didn't do anything particularly wrong. And let's run again our simulation. Then we have a couple of simulations. They're a little bit slower. This means that probably before I've done something wrong, but it's not a big issue. We can Jupyter notebook are nice because we can do this kind of exercise. We can use this as are lovely for sandboxes. Jupyter notebook are really lovely for sandboxes. Yeah, and now we have a better outcome and we have better metrics. Yes. Anyway, no big deal here. So I think in the interest of time and not to overload you, I think this cookbook, this little exercise could be useful for you. And there might be a lot of interest. If you look at the similarly named Py script in your folder, exercise folder, we essentially reiterate on the same concept, but we do a little bit more, like trying to start implementing things like parameter scan properly. And so in this particular script that we cannot run like a Jupyter notebook, we can do a number of things later on, but the first thing we do is we create again our analysis steppable, which is the copy paste of the one that we had before. So is explained elsewhere. We recreate the angiogenesis simulation. It is a copy paste of the one we did before, essentially. I'm sorry that I'm scrolling a lot of text, but I'm taking that you can really read this with calm, like when you're offline, and I don't want to overrun my time. But I want to get to a point.
Lorenzo, take the time you need. Better not to rush.
Okay, so I just want to highlight the last bit. So that is, once we have a class that works as we've seen before, no? Essentially up to line 341, from line 0, we have done exactly the same thing we have done up to here. So no big surprise. I know that I rushed since the beginning, since the time is short. So, but you have seen this thing with TJ. It will be really reiterating. What I think is interesting is that once we have our simulation returning matrix, we can do very funny things. And one funny thing that is optimization, as we said before. But to optimize, we normally want to have some strategy to sample our parameter space. And what you will see in this angiosim batch class is a toy model, is a toy exercise, again with angiogenesis model, again based on our matrix. and which explain a few things. One, how to create an instance of our simulation for parallel execution or sequential execution, or taking it and putting it somewhere, a new process that might be a node on our cluster. So we need this kind of stuff. And once we have a way to instance a simulation, then we have a way to run in batches. And this, if we do in a simple loop, simple Python loop, this will be serial on one processor after the other. One processor, you will do one of your samples after the other, or we can do in parallel with a slightly more complex code. And since this is, I'm sure that Pedro will go through it on Thursday, this is not the scope for today. I want to show you ways you can start playing with this and see how can you, if it works on your computer and things like that. Also, this is available in the exercise. And then there are sampling strategies. One is one at a time. One of my favorite and most useful times. You change one, you have 5 parameters and you change it across a certain range for a number of points, one at a time. And then you can do this for all parameters, and every time you generate so many simulations as your points. And then these functions don't do super CompuCell thing. They do just NumPy, NumPy, maths. Say, okay, that give me a series of numbers I can test my my simulation with. We have one at a time with inputs. If you know already that we want exactly certain values, we can give this. We have a poor man implementation of a Latin-hypercube sampling, which means that he scans homogeneously across your multidimensional set. If you have 5 parameters, you have 5 dimensions, and you will have homogeneously distributed samples across these 5 parameters. And that's pretty much it, because if you run this code as it is, and you decide about these numbers, you can change them if you want. You tell it how many CPUs you have. You tell me how many samples you want to draft for each iteration. So if you do one at a time sampling, I want to have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. No, well, sorry, these are the cases. In this case, samples, let me correct this before I tell you wrong things. It is iterations. So the number of times it does the same thing. Number of repetitions of the same parameter set. So this should save directly in your folder. So you should have already updated that. And that's really all that I got for today. If you run this code, things should happen pretty straightforwardly, and you will find a result. You will find that we have saved images in your in a folder that is the result folder, and you can analyze the data. And just for a note, just to tell you that stuff is there, if you want to go through it, at the end, I put in the Jupyter notebook again. If you have run this code and it runs, you can change the parameters, and you want to study a little bit how this parameter affects your data, you can do that playing with the notebook. And it's somehow self-explanatory. There are things that are commented, some that are not. Please take it with a grain of salt. I try to put everything without importing fancy libraries. So I think is a good, might be a good exercise book to have fun, not only with CompuCell, but with CompuCell generated data, and generate some plots that might be really easy to publish. They are publication ready, and that's all I wanted to say for today. So if you have any question, I'm happy to take them now or later if you want to rush to lunch. Okay? And thank you everybody for listening.